Hi all, I am Dr. M. Anuradha, Professor from CSE Department of SAEC Engineering College. Let us see about the concepts in the computer architecture. In the computer architecture, we are going to see about the performance as well as the instructions. So the performance, while doing the performance, we should know about the execution time. The execution time is referred as the total time that is taken by the processor or else taken by the computer to complete the entire task. This task includes disk access, memory access, IO activities, as well as the operating system overhead and the CPU execution time. And the throughput is referred as the total amount of work that has to be completed in a given amount of time. And bandwidth is referred as the number of bits transmitted per second. That is the amount of data that can be carried from one point to another in a given duration. And then next one is the clock cycles per instruction. This clock cycles per instruction is referred as the average number of clock cycles that has been needed by the instruction in a program. Here, the performance is considered as the execution time. The performance is inversely proportional to the execution time. If you are going to have more execution time, means the performance is lower. Whereas if you are going to have less execution time, then the performance is better. And hence, if you are going to have two computers named as X and Y, and the performance of X is greater than the performance of Y. The performance of X is greater than performance of Y. Then this is referred here as the performance of X is greater than performance of Y. But the performance is referred as 1 by execution time, and hence we have substituted here as 1 by execution time of X and here 1 by execution time of Y. Here you see here the execution time of Y is greater than execution time of X, and hence the performance of X is greater than the performance of Y. How much times the computer is better than the other one? That is considered here as the relative performance. So that relative performance we are going to consider as the factor n. That is the performance of x by performance of y is equal to n. This implies that x is n times as fast as y, then the execution time on y is n times as long as it is on X. For example, here consider A have the execution time of 10 seconds, whereas B have the execution time of 15 seconds. So now we can calculate how much faster is A than B. So for that we already know the execution formula, that is performance of A by performance of B is equal to execution time of B by execution time of A. Why here we had given execution time of B as the predecessor means here the performance of A is represented as 1 by execution time of A, whereas the performance of B is represented as 1 by execution time of B, and hence here the execution time of B by execution time of A, that is equal to n. Now the performance ratio is calculated by substituting the values. Here the execution time of B is 15 seconds, and hence here we have given as 15, whereas the execution time of A is 10 seconds, and hence 15 by 10. So that is equal to 1.5. This 1.5 represents the value n. That is, n is represented as how much times it is better than another one. So we can say that the performance of A by B is equal to 1.5, that is n times. So the performance of A is 1.5 times better than performance of B. Or else we can say the performance of B is 1.5 times slower than A. How we are going to measure the performance? For that, we are going to consider the clock cycle. Clock cycle in the sense, we are going to have the clock period. For example, to consider the clock cycle like this. So, here, this length of the clock period starts from here to here. So, this is referred as the one clock cycle duration. So, we are going to calculate the execution time for a program by means of using the clock period. So, for that, we are going to calculate, we should know about the clock cycles, CPU. That is referred here as CPU clock cycles for a program and the clock cycle time. This clock cycle time is referred here. This is the one clock cycle duration, and that is the positive signal as well as the negative signal. So this is one clock duration. So how many clock cycles the program use for doing the execution? So that's what referred here as the CPU execution time for a program. That is CPU clock cycles for a program in clock cycle time. We can represent in the form of clock rate also. Here, the clock rate as well as the clock cycle time are inversely proportional. That is, the clock cycle time can be referred as 1 by clock rate. And hence, we have substituted in this clock cycle time as 1 by clock rate. And hence, the CPU execution time for a program is equal to CPU clock cycles for a program by clock rate. Next, you can use the instruction performance. That is, by means of using the instructions, how you are going to calculate the performance. For that, we are using the factor clock cycles per instruction. That is referred as the average number of clock cycles per instructions for a program or program fragment. The program is considered as the collection of instructions. Some programs may have 5 instructions, some programs may have 100 instructions. So depending upon the count of the instructions, the total execution time, it will varies. And hence, by considering the instruction, how we are going to calculate the execution time. So the CPU clock cycles is equal to instruction for a program into average clock cycles per instruction. For example, we are having 5 instructions for a program, and for each instruction we are going to have 5 clock periods. So 5 into 5, so totally we will be having 25 clock cycles. So likewise we are going to calculate. If you are going to have 5 instructions and the clock cycles per instruction is 5, means for each 5 instructions you are going to calculate into 5, that is 5 instructions, and then for each instruction 5 clock cycles. So that is equal to, we are going to have 25 clock cycles. So likewise, by means of using the instructions also, you can calculate the execution time. So now our CPU performance equation can be executed as CPU time is equal to instruction count into CPI into clock cycle time. This instruction count is referred here as the number of clocks, that is number of instructions in that particular program, and this clock cycles per instruction here, it is referred as, here this CPI is referred as the clock cycles that are needed for each instruction. This one is the total number of instructions in a program. This one is referred as the number of clock cycles that are needed for each instruction, and what's the duration of the clock cycle for each clock period, what is the time duration, that is referred here as the clock cycle time. So this totally you are going to consider for the CPU time, and hence we already know about clock cycle time is inverse to the clock cycle rate, and hence this clock cycle time can be referred as instruction count into CPI, and this clock cycle time we have represented by 1 clock rate. Now we are going to consider the MIPS architecture. That is, MIPS is referred here as the millions of instructions per second. This MIPS architecture is a 32-bit architecture. Here, that is, for each and every processor, we will be having the separate instruction sets. So now we are going to consider about the instructions for the MIPS architecture. That is, the instructions are the words of a computer language. That's what we are calling it as instructions. Here, the processor, each and every processor, they are going to have certain registers as well as the supportive memory to hold the data as well as the instructions. And here, each and every instruction, they will be having some set of registers. That registers have to be mapped into the numbers so that we can represent in the MIPS instruction format. For each and every processor, they will be having certain number of supportive register. In MIPS, this is a 32-bit architecture, and here it is having 32 registers. In MIPS architecture, we are having 32 registers. In that registers, we are having the general purpose registers, temporary registers. Likewise, we are having different set of registers. That is, we are having the program counter, instruction counter. Likewise, we are having different set of registers. For each and every registers, we are going to assign the numbers. Here in the MIPS architecture, the registers, that is $S0 to $S7. These 8 registers are referred as the general purpose registers, and they are mapped on with the numbers from 16 to 23, whereas we are having 8 temporary registers that is named as $T0 to $T7, and they are mapped to the register numbers as 8 to 50. That is $S0 to $S7, that is referred as the general purpose registers, and they are assigned the numbers from 16 to 23, whereas $T0 to $T7, these are referred as the temporary registers, and they are assigned the numbers from 8 to 15. Hence, if $S0 here, it means it is mapped on to the number 16. If it is $S1 means it is mapped on to the number 17. Whereas if you are going to have $S2 means the number is mapped on to 18. So likewise we are going to map the numbers. So if you are going to have $S7, it is mapped on to the number 23. Similarly for the $T0 to $T7. Here for the $T0 we are assigning 8. So $T obviously will be having $T1 as 9. So likewise we will be having, so $T7, it will be mapped on to the register number 15. So by means of using these registers, we are going to do the various set of operations in the MIPS architecture. So this is the various, these are the various assembly language you are going to consider for the MIPS architecture. Here in the MIPS architecture, we are going to have different set of instructions, that is depends upon the different types of operations. First, we will consider about the arithmetic operations. Arithmetic operations, it involves the operation of doing the addition, subtraction. So for doing the multiplication and division, that can be done by means of repeated addition and repeated subtraction. For example, here the addition, if you are going to use the addition means, for that what's the instruction we are going to consider is add $S1, $S2, $S3. What is the meaning of this instruction in the sense? Here we are using 3 registers. In these 3 registers, for doing the addition, we need 2 datas. That two data we are going to store it in the $S1 as well as $S2. And after doing the addition, once again we have to store the result in the destination register, that is referred here as the $S1. So S1 is equal to S2 plus S3. Whereas for the subtraction we are using the sub mnemonics, and here also you are in need of two datas. That two datas you are going to have it in $S2 and $S3. Once again we are going to subtract the data S3 from S2 and we are going to store the data in S1. And here you are having another kind of instruction that is referred here as add immediate. Instead of having the two data in the two registers, you are going to use one register for storing the data, and directly you are going to give the data value in the instruction itself. So for that, in order to differentiate that, we are using add I. That I refers the immediate. If you are going to have I in the instruction, that is referred as add I, means here you should give the data. So what this instruction refers means, we are going to add the value 20. This 20 is a constant. This constant has to be added on with the content of the S2 register, and here you are going to store the result in the S1 register. So these are the types of the arithmetic operations that can be done in the MIPS architecture. Similarly, we are having the data transfer instruction. Data transfer in the sense, we are going to transfer the data from memory. Here we are storing the data in the registers. The other kind of data we can have also in the memory. So how we are going to transfer the data content from the memory to the registers? So for that we are using the data transfer instruction. Here this word refers, since MIPS is a 32-bit architecture, this word refers 32 bits. So 32 bits means we can either do the transfer of 8 bits, or else you can do the transfer of 16 bits, or else you can do the transfer of 32 bits. Since the word is of length 32, you can transfer the entire 32 bit, or else you can transfer only half of the word. So that's what referred here as load half, or else we can transfer only the 8-bit data. That's what referred here as the load byte. So here load word is represented as LW. So while using the memory transfer, memory for referring the data, here you are going to represent the data as load word $S1, 20 of $S2. Here this is referred as the offset address. This since in the memory, each and every location you are going to have a byte of data alone, and hence this word content will be having 32 bit. So totally for 32 bit, the memory, it will occupy 4 locations. Each location you are going to have as 8 bit of data. So 8 bit first location, second location another 8 bit, third bit another 8, third location another 8 bit, fourth location the last 8 bit. So likewise you are going to have 4 locations for storing the 32 bit data, and hence we are going to refer here the offset value. So $S1 is equal to memory of $S2 plus 20. So the corresponding word 20 plus the content of that register S2 is the address. From that address, you are going to transfer the content to the register S1. This load word is going to do the transfer of the data from memory to the particular register, whereas the stored word is just inverse of load word. Here it is going to transfer the data from the register to the memory, and hence we are using store word SW. Similarly, see here the data content from this memory address location is transferred to S1, whereas for the store word we are going to load the content from that memory, that is the register, into the memory. That is, from that register S1, the content is stored on to the location that is specified by 20 of $of S2. So this is 32 bits. The word is of length 32 bit, and hence we are using load word and then store word. If you are going for only 16 bit, you can use load half as well as store half. Similarly, you can use the unsigned values. If you are using the unsigned values, means you have to specify in the instruction as LHU. Similarly, for the byte, here this one is 32 bit and half is referred as 16 bit, whereas byte is referred as 8 bit. So these are the various set of instructions are used for data transfer. Similarly, the next category of instruction is the logical instruction. Logical instruction in the sense we are going to do the bitwise manipulation. Already know about the gate, AND gates, OR gates, NOR gates. We'll be using the truth table for that AND gates. So similarly here, the AND, OR, NOR, AND immediate, OR immediate. So these are the various logical operations you are going to specify. So if you are going to do AND, you have to write the instruction as AND $of S1, $of S2, $of S3. These are the various set of registers we have seen in the MIPS architecture. So what is the meaning of this instruction in the sense? $S3, that is the content in the register S3 and the content in the register S2 have to be performed AND operation, bitwise AND operation, and the concerned result have to be stored in the target, that is the destination register S1. Bitwise AND operation, OR operation, NOR operation. Here we have similarly seen the arithmetic operation, we have seen add and add immediate. Similarly, here we are using the and immediate. So if you are using immediate means we are going to specify the constant value instead of referring the register. That is the difference here. Similarly, we can perform the shifting operations also. Whether you are going to perform the register content in the left direction or else in the right direction. So for that we are using shift left and then shift right. So how many bits you are going to shift? So how many positions you are going to shift? That's what you are going to specify in the register. That is given as 10 here. And next one is the conditional branch. So conditional branch in the sense here normally in the processor it is going to execute the instruction in sequence. In sequence in the sense, for example, you are going to have the instruction, first instruction in first location, second instruction in the next fourth location. Why in the fourth location? In the sense each instruction occupies 4 locations since it is of the length of 32 bit. So after finishing the first instruction, it has to proceed with the second instruction. But if you are going to use certain instructions, it will change the sequence. For example, you are using branch on equal, branch on not equal, and then here branch on equal, branch on not equal. Here you are going to get 2 values. 2 values in the sense either you are going to get true or else you are going to get false. So for true, what else it has to do? If it is false, which equation it has to execute? So for example, you consider the branch on equal. Branch on equal $S1, $S2, $25. So what this instruction refers means if the content of the register S1 and the content of the register S2 is equal, then it has to switch on to some other location. That location is specified here as 25. So this offset value you have to consider. So 25 into 4. Each and every instruction you are going to have the length of 4. Hence this 25 refers 25 into 4, that is 100. And here, why it is given as PC plus 4 plus 100 in the sense, this PC is referred as the program counter. So, the processor, it is going to refer the address in the program counter in order to execute the next instruction. This PC implies it consists of the address of the next instruction to be executed. And hence, since it is given as 25 into 4, that is 100, plus the PC will be incremented by 4, and hence totally it will be going to PC plus 4 plus 100. So here the branch on equal, it is instead of switching from PC plus 4, it is going to switch on to the corresponding address that is specified in the instruction. Similarly for the branch on not equal. And set on less than unsigned, set less than immediate unsigned. Here you are using the mnemonics as SLT. So here, if you are going to check the condition, whether the content registers, two registers contents are less than, what else you have to set? Whether you can set the value as 1 or else 1. So what is the comparison you need means, whether it is equal or whether it is less than, like this you are going to do the comparison, and depending upon the comparison you are going to set the content of the registers. Set in the sense either you can set the value as 0 or either you can set the value as 1. Here you are going to check the condition, and depending upon the condition you are going to switch over. Whereas here the next category is the unconditional jump. Unconditional jump in the sense, in the jump instruction they are going to specify some address. On seeing this instruction, jump mnemonic instruction, it is switch over to some other memory address. So from that memory address, what's the instruction you are having, that has to be executed. So here you are having jump on register and then jump on link. Likewise you are having 3 categories. Here jump on address 2500. Already I have said each and every instruction it occupies 4 locations in the memory, and hence this 500th location it will be referring 10,000. Since 2500 into 4, each and every instruction it will be using 4 location, and hence 2500 into 4 now we will be getting 10,000. So J 2500 it refers, it has to switch over to the address 10,000. Next we are having the jump register and then jump and link, like that. Here jump register just it will, here it has switch on to the memory address, whereas in the register it is going to switch on to the corresponding registers. So how we are going to represent the MIPS instruction format? So the MIPS is a 32-bit instruction. Here you are going to represent the fields. Totally 32-bit you have to use. So here first one is represented as the opcode, and the next 3 fields that is represented here as the registers, and here you are going to have the shift amount and then function. First one, that is the op. It is referred here as the opcode. Opcode in the sense, what's the type of operation it is going to perform. In the previous instructions, we have seen that we are having data transfer instruction as well as arithmetic instruction, logical instruction, and then jumping instruction, branching instruction. So likewise, we are having various categories. Which type of operation we are going to perform, that has to be represented in the opcode field. And next follows the registers. In the MIPS, we are having 32 registers. So 32 registers, it is represented as 2 power 5. So this 5 is referred here as the number of bits that is used for representing the register. Since we are having 32 registers, 32 register is equal to 2 power 5, and hence for each register we are using 5 bits for doing the manipulation. And here you are having 3 registers. So for each register we are giving 5 bits, and here this shift amount. This shift amount we are going to perform the shift operation, whether we are going to have the logical shift left or right, how many positions we are going to represent here. For that we are going to use this shift amount. But for the register type and all, we are not, R type of instructions we are not using here, and just simply using the 0. Whereas this function is always referred as the function. Function code is used for doing the variation of the operation in the output field. For example, if you are going to do the arithmetic operation, so arithmetic operation here, for that opcode you are going to give us 0. Whereas in that arithmetic operation, what is the category we are using, whether you are going to use addition or whether you are going to do the subtraction, so that you have to differentiate by means of using the function. So that we have represented in the decimal form. Similarly, we can represent in the binary numbers. So the binary numbers means it should be have the combinations of zeros and ones. Since for the opcode we have used 6 bits, here you will be having 6-bit representation, and for the registers you will be having 5 bits, and then shift amount you will be having 5 bits, and then for the function code you are using 6 bits. So totally you will be having 32 bits. Since MIPS is a 32-bit architecture, we are using the 32-bit format. In the MIPS instruction, we are having 3 categories. That is, we have seen upon the type of operation, we have seen arithmetic operation, logical operation, data transfer, and then jumping, then branching. But here, the representation, instruction format representation, we are having 3 categories, that is referred here as R, I, J. This R is referred as the R type of instruction. R type of instruction means here in the instruction you are going to use all registers. That is for storing the data as well as for referring the data, all the inputs. Whenever you are going to perform the operation, you need the data. That data, all the data, we are going to have it in the register, as well as after performing the operation, once again you are going to store the result also in the register only, and hence that type of instruction are referred as the R type instruction. So in the R type instruction we will be having the output, whatever it may be, R type or I type or J type, we will be having the opcode bits as 6 only. As well as for the registers, you are going to have the 5 bits only. But how many number of registers you are using? According to that, you will be having the instruction formats here. So if R type na, you will be having 3 registers. For the R type, you are going to have 3 registers, and hence you will be having RS, RT, RD. 3 registers, 2 source registers and 1 destination registers. Whereas here, if it is an I type in the sense, you are going to have one of the data in register and another data you are going to give in the instruction itself. That is the constant value that we have already seen. So here you are going to use one source register and another sources as the constant value you are going to specify, and after doing that addition or subtraction, whatever it may be, once again you are going to store the data result in the register only. So here you need only 2 registers. So for the I category, you will be having the load and store also. In the load and store also, you are going to have the offset value in the register, and hence you are going to get that offset value and one data in the register, and from that you are going to do the transfer. So load, store, add immediate, it comes under the category of I. Whereas the next one is the J type of operation. In the J type, already we have seen J 2500 means you are going to switch on to the address that is named as 10,000, 2500 into 4. So that address you have to represent in the 26. That is for opcode, for 3 types of instruction you are going to have 6 bits. Whereas the remaining thing you are going to use for the registers as well as the constant and the address here. If it is a J type, now you are not going to have any register, and hence you will be using the address alone. So that's what given here. Instruction add, subtract, add immediate, load word, store word. So what is the format? Add, subtraction instruction. Here you are going to have all the data in the registers, and hence it comes under the category of OR. Whereas add immediate, load word, store word, it is going to use only one register, and another one is the constant value for add immediate, whereas here it is referred here as the address. That's what given here. In the load word and store word, you are going to have the address, and hence it is used. It is considered as the I type of instruction. So how we can do the translation of the mixed assembly instruction into a machine instruction? For that, you should consider, since we are having R type, I type as well as J type. If it is an R type instruction, you will be using the R type format. R type, for example, you consider add $T0, $S1, $S2. Since we have seen the numbers that are assigned for $S1, $S2 and T0 as various decimal numbers, that has to be represented here. Since it is an add operation, here in the opcode field you should have 0 for the arithmetic operation. Since it is an addition, for that the function code is 32. So that you are going to represent here. The remaining things here for the shift amount, since here you are not going to do the shift operation, it is referred here as the 0. Whereas the source value, that is the data, you are going to have it in $S1 and $S2. So this one you are going to have the value, since the registers have the decimal value of 17 and 18, that has to be substituted here, and the destination you are going to store it in here, temporary register. So for that you are going to have the value as 8. So that's what you are representing, that is you are going to do the conversion. Since here you have represented as a decimal, this can be converted into the binary form, and that binary form is stored in the memory. So how you are going to do the binary form means, here these registers, opcode you are going to have 6 bits, whereas for the registers you are going to have 5 bits. So this 0 has to be represented as 6 zeros. Whereas this 17 have to be converted as binary, and it has to be represented in 5 bits. So likewise, here for the 32 also you have to convert it into binary form, and you have to represent here. Similarly for the I type instruction, we are having 6 bits opcode, and then 2 registers we are using, and here you will be having the constant value for the I type. If it is a load word, store word instruction, you are going to have the address. If it is an add immediate, it is referred as a data. Otherwise, similarly, you will be having the opcode as 6 bits, and here for the registers, you are going to have the 5 bits. Similarly, here, this is the load word operation. Here you are going to have the opcode. For example, load word $T0, 32 of $S3. Here, since it is a load word, you are going to represent here as the opcode as 35. And for the registers RS and RT, this RS you will be having S3, and then here $T0 you will be having the value as S, and here this 32 is referred as the constant, or it is referred as the address. Since it is a load word, it is referred as the address here, that has to be loaded here. So these are the I type instruction. Similarly for the J type just for opcode you are using 6 bits, and the remaining 26 bits represents the address. So opcode for J, for example J 10,000, here you are going to have the opcode value as 2, and that address bits you are going to represent here. So for example, they have given the variables f, g, h, I and j are assigned to the registers. What is the compiled MIPS code for the following statement? Here this is the example, f equal to g plus h minus I plus j. So these variables we are going to assign it for the registers. And hence these are referred here. How you can rewrite this code as, here g and h to be added. So add $S1, $S2, and the result has to be stored in $T0. Whereas here you have to add I plus j. So for that, add S3, comma S4, $S4, and the result you have to store it in T1. So finally you have to do the subtraction, but the results you are having in T0 and T1. So just use sub $S0, comma $T0, comma $T1. So likewise you have to do the compilation code. Thank you.